afternoon to you all. Today I speak about refining Crotalaria juncea, relatively new biomass, very native to India, and its prospects of utilizing the waste glycerol for making succinic acid. Well, our aim is to develop and design a biorefinery based on Crotalaria juncea as the feedstock. Now, Crotalaria juncea is very native to India, and the seeds are mostly used as animal fodders, but they grow plenty, and there are fibers which have got interesting chemical composition which can be utilized to make fuels or some interesting intermediates. If we start with the standard delignification, enzymatic hydrolysis, and then fermentation route. But that I will not be talking today in this lecture, but we are handling both the seed and the fibers in two different projects. For the seed side, we have started with extracting oil from the seed, and then after extraction of the oil, we have tried to transesterify it to make the diesel, and glycerol, as you all know, it comes as a waste. It becomes a waste glycerol because there is huge glycerol produced there when we transesterify, and we try to utilize the glycerol but not as a crude. We purify it using a sequential desalination technique, and then we utilize it for making succinic acid on a fermentation route by using some strains, very common strains, some patented strains, and also some common strains being used in an anaerobic mode. And then we utilize the succinic acid to make 1,4-butanediol, BDO, on a high-pressure hydrogenation setup, which is almost in the pilot scale. And we are trying to investigate on very specific aspects of the entire route up to 1,4-butanediol. Now, this is the end point for us till now in the seed side. And in the fiber side, we have collaborated with NTNU of Trondheim, Norway, a Norwegian group, and SINTEF, which is Norway's Energy Institute, and they are using some spruces, Norwegian spruces, and we are using juncea fiber. After delignification and enzymatic hydrolysis, we found that mostly xylose is present there in the composition. A lot of xylose is present, and we are using obligate anaerobes to utilize that xylose to make butanol and butyric acid, and ultimately we have a plan to make butyl butyrate. So that's the fiber route, but today I will be talking on the oil route, and in the oil route, the specific attempts, the novel attempts which we are taking is simultaneous extraction of oil and gum. There are a lot of gums produced, so we have devised a new room temperature based technique based on three-phase partitioning, which I have talked in the morning in the macromolecule session, where we have extracted oil and gum simultaneously, and this gum has got properties, chemical and physical properties very similar to guar gum, and these could be utilized in cosmetics and food industry later. And then we have also devised a new Soxley apparatus where we have implanted an annular packed bed inside the Soxley apparatus, because all of you know that Soxley operates in two regimes. One is a downflow regime when the vapor condenses and pours down the thimble, and in the second regime, purely due to hydrostatic action, it goes up till it gets siphoned out. Now, in the annular packed bed, the advantage of using an annular packed bed is that in the upflow regime, if the packed bed diameter is too big, then the upflow regime, the seeds which are inside in the core of the stem, it could be attacked by the solvent from both sides, from inside and outside. Now, on the scale up of this system, I will be talking tomorrow in another session around 4, I think in between 4 to 4:30 in the main conference. And so that's a novel attempt of how we can optimize or maximize the extraction of oil and make it continuous and make it more interesting, and we have less amount of waste. So that's one part of it. And then when we are making 1,4-butanediol, we are now playing on the combination of catalysts, and the combination of catalyst and catalyst base materials or seeds, and trying to optimize the selectivity of it towards the production of 1,4-butanediol in comparison to tetrahydrofuran and gamma-butyrolactone, which are very natural intermediates in the process of succinic acid high pressure hydrogenation to make 1,4-butanediol. So these are the two things we are working on. And the succinic acid, in this particular talk, I will be mentioning on how we produced succinic acid using the standard fermentation route. We have used very simple standard strains like E. coli. We have used engineered E. coli, and we have used engineered E. coli in an anaerobic fashion. And we have data for patented strains also, like Mannheimer succini producers and all, but because people have used big research groups, US-based research groups in Michigan State University, they have used those strains to make succinic acid, so we have not gone into that line. And so the overall aim is to make a biorefinery using Crotalaria juncea. Now, the talk will be mostly dependent on this. Is not very business-like talk. It will be more or less academic. So I've got 4 major methods which I will be talking on, but very briefly talking on the first 2 methods, mostly go to the kinetic part on the microbial growth. So these are the juncea seeds, and this is a standard biorefinery known to almost everyone, and we produce a biodiesel, but what we found that the oil which is produced has itself is a fuel, and we have published it in the Journal of Fuel, which is published by Elsevier. You can see that publication about 2.5 years back we published that. So juncea oil itself is a biofuel, and we found that the diesel properties are not very far from the oil. So we tried to utilize the glycerol more, and these are the derivatives of glycerol, which known mostly to all of you, and main uses of succinic acid in pharmaceuticals, textiles, food industries, agriculture, photography, cosmetics, almost everywhere. And the market price varies a lot. When we started off thinking on this project back in 2008, I had all the PhDs, most of them were part-time, so we took a lot of time to progress to a reasonable platform. And then we started with the transesterification of the extracted oil using various types of natural and standard catalysts. For natural catalysts, we used cappies and conch shells, which are plenty. I mean, they don't cost anything, practically zero in India, in my part of the country. And then we purified the waste glycerol in using several physicochemical techniques. And then we studied the growth kinetics of E. coli, both engineered and normal E. coli, using crude glycerol, commercial glycerol, and purified glycerol. And we found that purified glycerol, results of purified glycerol and commercial are very, very close. And then we did the fermentation, and we optimized the process on a statistical basis using central composite design. Now, this is the normal Soxley extractor. I'm not going into the special design which we have done, which I will be talking tomorrow. So the crushed seeds are put in the thimble, and oil gets absorbed by the solvent. Oil gets leached out by the solvent, rather. And then these are the same images of conch shell and cappies which we have used as the catalyst. These are the XRD images of locations of calcium in the shell, conch and cappies. And these are the FTIR patterns which show some functional groups also present, so that esterification can be enhanced or duplicated like the normal methanolic KOH route. And ultimately we, in a very laboratory scale, we make the diesel, and then we find the catalyst activity, and we find that cappies and KOH both give more or less similar activity, both based on initial rate method. Now the reaction mechanism is very commonly known to most of you, so I will not elaborate on this, but calcium oxide based catalyzed reactions look like this. And ultimately these are the fuel characteristics of the diesel, and the calorific value is, the last row is for Junkia, which is about 37.68 megajoule per kg, in comparison to Jatropha, which is 40 to 42 megajoule per kg. And these are some of the methyl esters as estimated by the gas chromatograph, mass spectra based data, and we have these acids present. By using different catalysts, we get different acids present in the system. Now, fatty acid content of the sunhemp and other biodiesels, if you compare, then you can see from this picture what's the difference. So you have the soya bean one, where we mostly have the stearic acid in our system and palmitic acid after transesterification. So we found that diesel part is not that lucrative from commercial point of view from the values of the acids present. So we tried to develop things based on this is the process optimization, and we found in the best possible way how we can make the diesel. So we optimize the diesel production using by modulating the mole of methanol, then catalyst concentration, type of catalyst, and with the optimized value, we repeated the experiment, and we found that the production yield of the diesel match very fairly. And next we go to the purification of waste glycerol, which is based on this. We have got the sunhemp oil and then alkaline methanol for transesterification. We do a simple phase separation, and crude diesel is taken out, and with crude glycerol we first recover the alcohol, and then we acidify with phosphoric acid, sulfuric acid, hydrochloric acid, and perchloric acid and acetic acid. And then after decantation, free fatty acids are taken off, salts are taken out, and then we neutralize with sodium hydroxide, and again the system is desalted, and then we perform solvent extraction, and again the system is desalted. And we remove the color by simply using by simply using activated carbon, and then we do a vacuum filtration to get a concentrated purified glycerol. And we have compared these properties, pH, glycerol content, ash content, and now our purified glycerol's ash content is, the best method which was optimized is using phosphoric acid that is based on trade-off between buffering and common ion effect. We could establish that phosphoric acid performs the best for purifying glycerol. Ash content is still is very high for crude glycerol, whereas for purified glycerol using phosphoric acid it is reduced to 0.23, and then glycerol content is also quite impressive. It is 94.4 as compared to the commercial glycerol, which is 99.01. And then we have the non-glycerol organic matter. We give these values because these could be the inhibitors for the microbial fermentation. So the more we purify glycerol, the more it is, it is better for there will be less inhibition in your system for microbial fermentation. And removal of color, we have compared with activated carbon and bleaching earth, and carbon still gives the best result. And if we compare the purity of glycerol, we have compared using GCFID based method, which is the most standard analytical method, and also spectrophotometric based method. And we found that these are some of the fatty acids present in the purified glycerol in comparison to the impure glycerol. And ultimate purification we have done using a membrane, but before membrane and after membrane separations give more or less the same type of fatty acids. If you compare, then it is before membrane and after membrane, few things are reduced, but we have octadecanoic acid, which is octadecanoic acid is almost 0 for purified glycerol after membrane. And these are the reactions which are mainly taking place for simultaneous desalination and extraction process. Now, main inhibitors in the crude glycerol are the remaining methanol, then mostly soap, if a lot of potassium hydroxide is used than estimated, and then some acids which could be the inhibitors. So we try to remove them, and these are the reactions with acetic acid, then sulfuric acid, phosphoric acid. And we find that we run a central composite design for and an ANOVA analysis for giving a statistically optimized situation with respect to the choice of acid, then pH and amount of adsorbent. And we find that this is the model which is giving the predicted level using multiple regression analysis, and response surface plots give the optimized scenarios. Type of acid and pH for 0.87 gram of adsorbent, and type of acid and amount of adsorbent at pH 3.5 for the purity of glycerol. Now, we find the optimum condition to be like this. Type of acid chosen is phosphoric, statistically optimized, pH 3.26, amount of adsorbent 0.933, experimental value is 91.14 and statistical value is 90.4. So they are very close. And next, I go to the various aspects of Escherichia coli growth kinetics. Now, there are growth kinetics we have studied using some models, mostly inhibitory and non-inhibitory in nature. And we found that for purified glycerol, the non-inhibitory models, they performed very well, whereas for the inhibitory models, they performed quite well for crude glycerols, where there were many inhibitors present in the system. And we found that the Iba-Edward model, it performed well for the non-inhibitory case. So these are the values. If you see the evolution of concentration of biomass with respect to time for different initial glycerol concentrations for commercial, purified, and crude, these are the results. Now, statistical analysis, again, we have performed for the residual. So this is not a model based, simply what the model gives and what our experimental value gives. Just that difference we have found out as, and that is given as the residual. And these are the models, and ultimately effect of glycerol impurities say high concentrations of monovalent salts influences the transportation of nutrition factors through the cell membrane. Stearic acid present in the fermentation medium aligns with the fatty acid tails of the membrane. Oleic acid causes a kink in the molecule which hampers the diffusion of nutrient factors and metabolites through the membrane. Linoleic acid, a compound with a high degree of unsaturation, has two kinks which cause the inhibition of nutrient factors and thereby limit the synthesis of succinic acid. The unsaturated fatty acids with two or more double bonds which are present in the crude glycerol have strong influence on the diffusion of the substrate along the membrane. And lastly, we purify the succinic acid and optimize the purification process. This is the pathway for formation of succinate, and glycerol utilization pathway in the bacteria is this. Is the metabolic pathway within the bacteria, and these are the levels we have chosen, and we have used a design expert box Benken scheme to where the factors were type of glycerol, pH of the media, incubation temperature, yeast concentration and peptone concentration, and inoculum density. And we found that the optimum value ranges of parameters varied in between these ranges, the parameters varied, and ultimately we found the yield of succinic acid from Junkia seeds is 20% with the engineered E. coli. And with anaerobic we have done only couple of experiments and it is 35%, but we are not yet establishing, but we are doing it in a batch scale, and we expect a better result using simple E. coli. So that's what I wanted to say here. There is not much difference in the growth kinetic parameters for purified and commercial glycerol. So first one can be used as a replacement of commercial glycerol. And we are now scaling up the purification of glycerol stage, that is sequential desalination extraction process. We are scaling up, and we are still doing the fermentation on a batch scale, but we have 3 continuous fermenters. Maximum size is 30 liters in my laboratory, so we will be scaling up that in that system. Now, I am more interested to collaborate with groups who will be interested to work on the scale-up side and process automation, like quite a number of steps in the complete process are in the batch mode. So, and some of them are in the continuous mode. So I'm planning to do a full continuous scheme to establish this biorefinery, seed-based biorefinery. And I expect to interact with you after the session. And I finish my talk here, and I will be glad to answer if you ask any question.
Okay, thank you. You took all of your time, so what we will do, I think you will come with us at the cocktail after, so she will be available for questions. So thank you again.
Thank you to CRIBIQ for inviting me, and I just briefly mentioned my contact with Quebec. For past 7 years, I have been having a collaboration with Professor Diogo Coucave, who is the head of the Department of Applied Chemistry and Chemical Engineering of University of Quebec at Chicoutimi. And 3 of my students, they have done their PhD there, and 1 postdoc is still there, and 1 PhD has gone back to India, and she is a colleague of mine now. And she's a co-principal investigator of the Indo-Norwegian project. She's taking care of the delignification part because she worked on delignification for some wood processing things. Her PhD was on wood technology and preparing processed wood and surface modifications. Okay, thank you.
Now about letter. Thank you very much again.